Okay, so we're going to briefly talk about fundamental properties of NNMs briefly today, and then we're going to go through a lot more of it on Thursday. So basically, there are 5 properties or fundamental properties, and now we're working with Rosenberg's definition from now on. We're considering Rosenberg's definition. First, they exhibit frequency energy dependence, meaning that their frequencies change with respect to the energy in the system. Their modal interactions arise. These are internal resonances between different NNMs, and we will, at the end of that second property, we'll give an extended definition that accounts for internal resonances. The third is that NNM bifurcations exist and nonlinear normal modes have stabilities. So sometimes an NNM can be unstable, sometimes it can be stable, which is contrary to linear normal modes, which are always stable. They're neutrally stable. We'll briefly look at the deformation of the FRF at resonance, and then we'll very briefly touch on invariance. So today we're going to start frequency energy dependence, and this is just a typical feature of nonlinear systems, specifically that there is frequency energy dependence exhibited in their oscillations, meaning that the frequency of oscillation will change with respect to the energy in the system. And one consequence of this is that the frequency response functions are no longer invariant. And that means that in a linear system, if you compute a frequency response function, which is effectively, if we're thinking from a data perspective, you compute the fast Fourier transform of the response, and then you divide that by the fast Fourier transform of the input, which is usually some type of impulsive input from like a modal hammer, or it could be a harmonic or something random from a shaker. If you do that for a linear system, then what you'll find is that the FRF is the same regardless of what amplitude the input takes. We're just thinking from a hammer test, if you hit harder, you get back the same FRF. That doesn't change. That's what we mean by invariant here. For nonlinear systems, if you hit harder, you get back a different FRF. The FRF changes, and this is where we'll see this when we talk about 4, and I'll show an example of that. Actually, I'm going to show it right here, now that I think about it. So we're going to consider system 1 here. As shown here, this is just a simple 2-degree freedom system with linear coupling, linear dampers, linear springs and linear dampers, both grounding and coupling, and then a single nonlinear grounding spring shown there. The equations of motion for this system are going to be x1 double dot plus 0.02 x1 dot minus 0.01 x2 dot plus 2x1 minus x2 plus 0.5 x1 cubed. That's then equal to f cosine of omega t. You'll notice here the damping is relatively weak, which is typical for vibratory systems, but the linear stiffness, and in this case the nonlinear stiffness, is not weak in this regard. The second equation is going to be x2 double dot plus 0.02 x2 dot minus 0.01 x1 dot plus 2x2 minus x1, and that's equal to 0, and we can call that 13b. All right, so if we go ahead and compute the FRS, in this case done numerically, what you end up with is curves that look like this, one for x1, one for x2. This is for omega close to the first resonant frequency, and effectively we have increasing force going in that direction. And as you can see here, that this frequency response curve changes depending on that forcing level. If we do the same thing, but now for omega close to the second resonant frequency, we again get these deforming or changing FRFs, as you can see here. So the higher you force the system, the FRF is going to change as you increase that forcing, which then illustrates the energy dependence. If you increase the force, you're increasing the amount of energy that you input into the system, and therefore changing how it responds. And all right. So you can also show this for different initial conditions, that the NNMs will change in the configuration space as you change the initial conditions. I did not include the MATLAB code for this, but I can provide this somewhere, probably as a separate file. So here on the left, we are starting with the two masses having the same initial displacements. And in this case, the NNM is just a straight line, so we could probably conclude that this is a linear normal mode response in this kind of case, or nearly linear. If we increase those initial displacements, we start to get curvature in the NNM curve as shown in the center plot. And if we increase that further, we get more curvature as well. And so these are just changing as functions of the energy, since in this case we're increasing the initial displacement, we're increasing therefore the energy in the system. We are also going to use, in worksheet 2, we're going to use what's known as the method of harmonic balance to study this frequency energy dependence. And that is what we're going to do today. Okay.